So welcome everyone to the third Hardware Acceleration Working Group meeting. In this meeting, essentially, we will treat a number of topics, and we will then have a guest speaker, which will be sharing with us a very interesting topic for approximately the last 30 minutes. As we did in the past, I'd like to open up the mic for all of those of you who are new to the working group and which would like to share a bit what's your work, how are you interested in hardware acceleration, and essentially just say that, and we'll try to do our best to welcome you. So those of you new, please, those of you that want to new to the group, feel free to introduce yourself.
Yeah, hi. So maybe I start. So I'm Sören, I'm from PLC2, and I'm there the site owner of the Frankfurt team, and I have a strong background in computer vision applications on FPGAs, and I recently also held an introductional talk into ROS and ROS2 as a webinar for PLC2 some hours ago, and yeah, I'm also in with FPGAs and Xilinx, and I'm there to see what is going on and to test the approaches from Xilinx, because I have a longer background in acceleration of FPGA stuff. Yeah, and I'm just interested and want to follow all of that. Thanks.
Thank you, Søren. Welcome.
I guess I'll go next. My name's Lou Amadio. I'm a principal dev lead at Microsoft. Been a member of the TSC since the very beginning. We contribute to a number of different things, including ROS on Windows as well as ROS with Azure. And we have a set of ROS nodes around using the Onyx model or Onyx runtime for hardware accelerated inferencing. I'm actually joined by Jerome Shang, from Microsoft, is not Shang, Jerome from Microsoft as well.
Thank you, Lou, and welcome. Hello, Jerome.
Hey, sorry, I had some connection issues. I'm part of Azure Edge Device Platform and Services, and I have a specialty for hardware in picking, influencing, or defining our silicon needs. And I'm sitting here because I read that hardware acceleration can solve most of your acceleration gaps from computing to actuation.
Great, you're in the right group.
I think I can go next.
Please.
Hi, I'm Kunal. I am one of the current maintainers of PCL. My current work essentially involves accelerating specific parts of our robotic software stack using different kinds of nodes. So we have some nodes which are using Onyx runtime. We have other nodes which are essentially CUDA cores. And then we have our own main CPU, which is x86 based. So, I mean, this is pretty related to hardware acceleration, so I thought I would join because it looks to be on a similar track, especially based on the discourse discussions.
It is fantastic to have you, Kunal. Welcome. Anyone else that wants to introduce himself or herself?
I don't think I introduced myself last time. I'm Greg. I'm at Open Robotics. I'm mostly just acting as a listening ear for this group to see how things are going. I'm also pretty interested in hardware acceleration, as I am working on the Open Vision Computer project, which is based off the Zinc chipset. So nice meeting you.
Awesome. Great to have you, Greg. Thank you.
I guess I can also do a quick intro. I'm Brian. I work with Sabrina. We're going to be talking a little more later, or she'll be doing more of the talking. So I'll let her introduce herself. But we're at Harvard, and we work on acceleration for motion planning at the moment, but just robotic stack in general, hardware acceleration, GPU, FPGA, whatnot. How can we move past the CPU with the robotic stack to get real-time performance?
Thank you, Brian, and welcome.
Hello, maybe I can take the chance to introduce myself. I'm Alessandro Capotondi. I'm senior researcher at the University of Modena and Reggio Emilia. Actually, I think in the call today, there are also some our collaborators that work with us. We have a strong experience on autonomous vehicles, and I personally have also experience on hardware design. And so we are really interested on, our research now is to support our technology of the autonomous driving from GPUs to Xilinx FPGA. And so we are really interested on ROS for FPGA SoC. So this is something that we already do, and I think your job is a good job. It's a really nice initiative to support well this kind of technology.
Great to hear, Alessandro. Very welcome. Okay, last call. Anyone else?
I'll just take a second to say hi, but you'll hear more from me later. Just hi, I'm Sabrina, and again, I'll talk your ear off later, so I won't take up more time now.
Thank you so much, Sabrina, and welcome as well. Awesome. All right, guys. So let's kick it off for about 20 more minutes until we give the mic to Sabrina, who's going to tell us very exciting stuff. I just pasted in the chat for everyone the meeting notes of today. As always, this meeting notes will be updated after the meeting, including the recording, the slides, and etc. So feel free to make comments. Unfortunately, the permissions that we have given so far are just commenting permissions, because there's been a couple of persons already who have removed the content wholly. I don't know why, but we decided that it was best to essentially allow people to give suggestions and make edits in that manner, so that we avoid people removing our work for the past few weeks. So that's there. So after the welcome and intros, I wanted to throw a piece of news. Who is the first one that's highlighted in here in yellow, if you're looking at the minutes. So Soren, who introduced himself, gave a fantastic talk about how to use hardware acceleration capabilities and technologies for ROS. He gave a very nice overview of ROS overall, and also essentially about the projects they've been doing, and particularly he shared very, very interesting results when using it with the perception stack. So if you wish to learn more about how to use hardware acceleration with the perception stack, definitely check out Soren's work and PLC Choose work. Worth watching indeed. So after that, let me jump directly into the first of the topics, which is the REP 2008 review. I'm going to share my screen real quick in here. There we go. And to have a quick peek at REP 2008, which is something we're working, and we've been working for a few weeks now, and where we encourage and invite people to make contributions. There's a bunch of you who have already have commented and gave suggestions. Thank you for that, and please keep it up. The REP, for those of you not so familiar, REP stands for ROS Enhancement Proposals. It essentially can be defined as the conventions and definitions that essentially ROS2 packages and the community should follow when it comes to building ROS2 computational graphs. There's a bunch of them. You can check them out if you wish. This one particularly aims to somehow shine some light and somehow lead the way into how we can, as a community, as a group, jointly build hardware acceleration capabilities that are interoperable, that are technology agnostic, meaning that you can bring them from FPGAs to GPUs to even other technologies. So that's pretty much the vision we are trying to fit in here. It's built, again, in a technology agnostic manner, and also in a platform agnostic manner, meaning that we are not just tackling specifically deep embedded boards or the edge, that it's nowadays just so called. We're also looking at workstations and even data centers, which will come down the road, but still we did design the architecture with this in mind. And that's what's proposed in here. So the official way to get engaged with this, read more about it and comment, give your views, is in this pull request, which is listed in the minutes. You can check the files directly. I'm just giving you a sneak peek of how it looks if rendered according to the reps repository. And in a nutshell, again, in the abstract, we do describe what I just went through. It's very important to highlight real quick the value for stakeholders. And this is one of the key aspects of how we are trying to make it technology agnostics. We are trying to leverage value and create value not just for package maintainers, which are very important stakeholders within the ROS2 community, but also for consumers, that is any of you building ROS2 computational graphs, and finally for silicon vendors, groups like NVIDIA, like us, like AMD, like many others like Renesas, who essentially want to add value to the ROS2 community, and we need to somehow build up a recipe, a series of guidelines that allows others to jump in, to add value, to contribute, and do it in a constructive manner, not in a, let's say, way that creates even further forks and further fragmentation, because some of you know already ROS2 and ROS overall is quite fragmented. So here are also some of the anti-goals about what we think we definitely don't want to treat, and this is open for discussion. And this is, again, a short definition and description of the architectural pillars wherein we had built these conventions and proposal. This was somehow also touched into previous meetings, so if you wish to learn more, also encouraging you to check that out. I will essentially
Victor, you are sharing just a code, not a document. I don't know if you wanted to share a document.
I changed my screen and I didn't notice that. Sorry. Sorry. Please interrupt me if that's the case. That code was surely interesting. So essentially, again, the document is over there for you to review and to go through it. One thing interesting that I'll encourage you to take a closer look at is how we have categorized acceleration kernels. We are dividing kernels into 3 levels, 3 big groups, which go against first ROS2 application libraries. That's any of the ROS2 stacks, manipulation, navigation, perception, whatever. That's the first big level. Then the ROS2 core packages, that is the core ROS2 layers, RCL, CPP, RNW, and even parts of the corresponding middleware if appropriate. And then we have underlayers, ROS2 underlayers, which go from the middleware all the way down to the data link layer, including, of course, possibilities such as Ethernet, TSN, time-sensitive networking, EtherCAT, and others. Those ones also need to somehow be ROS2 connected so that we get an end-to-end ROS2-centric stack that can provide determinism. So that's something I encourage you to review. And also something that I wanted to bring your attention to, because we will briefly touch it today, is benchmarking. We have proposed a benchmarking architecture that tries to propose a way to do benchmarks when it comes to hardware acceleration. Particularly, it proposes to do things in a non-functional and gray box manner. And you have a description in here of what that means and why we are essentially suggesting it that way. So please feel free to dive in and share your thoughts. And finally, after evaluating a number of technologies, the selected one so far for instrumenting the whole stack from, again, the data link layer all the way up to the application layer is LTTNG, the Linux Tracing Toolkit, next generation, which again is vendor agnostic. It works fantastically fine. And there's some very interesting ongoing work to instrument things farther beyond the CPU computations, going down to some of the aspects within the GPU and some of the aspects within the FPGA. So that's something we are also looking at. I'll leave it there for now on this quick pass and review of this rep, but encouraging everyone to have a look, to share feedback, and particularly if any of you, and I wanted to raise these 2 topics for discussion today for a reasonable time. The reason why we are pushing this so hard is, and hopefully these 2 topics will shed some light into this, is because we are realizing there's a number of things that will create somehow misunderstandings. So, so we'd like to tackle them the earlier, the better. The first one, which is connected to the daily work that I do, is extending existing ROS2 packages versus integrating that essentially hardware acceleration into existing ROS2 packages. And here is an example. The folks from NVIDIA who are with us here today forked image pipeline and did a great work, I think, by essentially providing capabilities to be able to run it on GPUs. There's some ongoing work on our direction from Silence's perspective on that as well. But there's a big question mark in here, which is, do we fork that repository and somehow fragment the maintenance of this code? or do we try to integrate hardware acceleration directly into the repository? And we don't claim, I don't have the best answer for this, but I definitely would like to hear others' opinion, especially Gordon and Hemal. I think you guys are in the audience, so it would be great to hear your views on this, and maybe someone else's as well. Maybe Greg from Open Robotics, what's your take on this?
Yeah, yeah, thanks for raising this, Victor. I think NVIDIA's focus here is really around trying to provide an entire package that developers can use, and they don't have to deal with the problems of getting it working. And I think our priority is making sure that we can get hardware acceleration into the hands of developers. So maybe the one concern I have with the work we do in the working group today is that it's entirely focused on compilation within a single node. And that, unfortunately, is not our bottleneck in ROS2 today. Our bottleneck in ROS2 is building a graph or pipeline of nodes and providing hardware acceleration between nodes. And so that's part of the work that we're doing with the Open Robotics. That's part of our Open Robotics effort that's being developed for Humble. And it would be good to have this working group participate or collaborate and contribute to that effort. I think the focus entirely on compiling your node is a little short-sighted.
And that's a great input. And for context in here, essentially what Greg is referring to as limitation for what concerns computational graphs is that both GPUs and FPGAs essentially have a limitation with the existing ROS2 architecture, because it's CPU centric, and every single time that information flows from one node to the next one, it needs to go through memory, and that involves the CPU. So what Gordon is pointing out is that they are working on trying to avoid that by essentially making some adjustments. These adjustments are purely implemented around Rep 2007, which actually is the type adaptation technology that Open Robotics pushed forward. We are doing the same, Gordon. So I am more than happy to bring that up. The way to do this in an organized manner is feel free to reach out, feel free to bring up this topic for the next working group meeting, and commit resources, commit person power, and you'll definitely have as much time as you want for this, because that's what we want to encourage in this working group, to give people a chance to contribute in a technology agnostic manner. And I think that's what you're pointing out. So definitely thumbs up for that. And one thing we can try to reproduce, and that's a suggestion for engaging with that work, is other working groups are kind of like focusing contributions from different vendors, even as it is in this case, around the same computational graph. They are defining kind of like a reference computational graph that different technologies try to improve. And in this case, we could try to do that. And if you have any suggestions on that, Gordon, that's a fantastic first contribution to define the computational graph, maybe aligned with what you guys have already shared publicly. And I think that's going to be very exciting to cooperate on. Maybe returning back to the question, I'm still curious about what folks out there think about forking ROS2 packages as opposed to contributing directly to some of the existing ROS2 packages. There's a big but in here, which is that if we start forking things, then maintenance is going to become a nightmare. And also the second but is licensing. The fact that forks sometimes change the license or rewrite things changing the license becomes a somewhat conflicting issue. So I'm particularly interested, Greg, you from Open Robotics, have you guys discussed any of this? What is the official recommendation when it comes to contributing? And do you have any ideas so far on how to integrate hardware acceleration into existing ROS2 packages?
I'm not involved in this particular project, so I cannot particularly comment from an official standpoint. I think just from a community perspective, like there's always, I mean, I think you're saying fragmenting is to go to a minimum, but I mean, for a particular project, right? Like sometimes it's not time. Trying to make a perfect solution can be difficult, I imagine. So, you know, I think it comes down to like, what's the time involved and what's the priority? I think you know, it's up to whoever wants to put in the effort, right? If the effort's in interest of, you know, if somebody wants to fork it, they can fork it. If they don't want to fork it, they don't have to fork it. I think it's like up to the individual and if they're willing to maintain what they've made. But you know, from a community perspective, I think it is always optimal to try to aim for less than more. But like I said, it's case dependent.
Okay, no, that helps, and let's keep the conversation open and say if anyone has thoughts on this, please make sure to send them to me, and if necessary, I will reopen this topic. This is something we as a community, as a group, need to somehow get together on, because otherwise we'll suffer down the road. And this is also connected, by the way, to the second item I prepared in here, number B in the second agenda item, which is what's the preferred mechanism to create ROS2 nodes that support hardware acceleration as a feature to be enabled either at lunchtime or at runtime. And the rationale behind this is that essentially we want to release hardware acceleration hardware. So we want to release the FPGAs or the GPUs sometimes, and these resources are limited, by the way, in most platforms. We want to release them depending on certain environments and depending on certain situations within the robot. We may want to release them from certain tasks so that we want to enable or disable hardware acceleration in specific nodes, again, even at lunchtime or at runtime. So there's a couple of thoughts in here, which I dropped into the meeting notes. It would be awesome if anyone has any ideas on this, because again, we are still at the design process right now. And hopefully some of these can land into the REP 2088. So that's a great thing where to contribute and send your ideas. But this is definitely a topic that concerns me, because again, we wanna engage and disengage hardware acceleration with particular nodes. And there are many use cases for this with real robots. So that's yet again another reason why we think that, or at least I think, I speak on my behalf right now, that I think that essentially trying to avoid forks and contributing with the existing open source licenses to existing ROS2 packages and stacks will down the road prove to be the best strategy. But again, happy to engage into further discussions. Now, real quick, the third item into the agenda is a recap of the progress so far. And well, so far we're having not so much folks actively putting their time. It's essentially being Pedro and myself. And if you want to follow up with that, I encourage you to take a look at the, so within ROS acceleration community repository, we have, and we are maintaining a project board, and it was requested in the past by one of you, so thank you for reminding me that. And this project board shows progress. So if any of you is willing to put some of your time or want to engage with this and want to learn more, picking one of these tickets and starting to put your time, that's the right way to go. And if you have questions about what to do, feel free to open a ticket or ping me directly, and I'll give you some work. That's it. So since we don't have much time, I was planning to give you a sneak peek on some of the updates related to how we from Xilinx released a number of updates to simplify ROS2 embedded flows. It's very important to accelerate individual nodes. It's very important to accelerate computational graphs, that is transition across nodes, and get 5x, 10x, 100x of acceleration. But if this is only usable by a very, very few experts, it becomes essentially unmanageable. So what we've been trying to do incrementally is to lower the entry point barrier by facilitating tools that are integrated as first-class participants in the ROS2 ecosystem, particularly as extensions of the AMENT build system and the colcon build tools. So you can take a look at this. There's a bunch of them. We're working on more, and feel free to send input, send feedback, and related. So that's one. The second one, and apologies for going so fast, but we are time limited in here. But the second one, which is still an ongoing work, I haven't closed this one, hopefully soon. It is pushing publicly the benchmarking architecture that I described before while going through REP 2008. So this is today demonstrated with a number of the acceleration examples we have pushed publicly. if you want to have a look, take a look in here. And then in the coming few weeks, possibly I will find time to document everything and provide tutorials, which we will make available for everyone. Now, with time left, I wanted to touch into an ongoing effort to port the architecture we have come up as a group to a new board, to a new hardware platform, the Ultra 96 V2. Pedro, are you with us? And would you like to share a few bits of your work so far?
Okay, trying to be fast because we have not so much time. I identified the files to need to be modified to build a Ultra 96 board. There is no so much files for the recipes. The problem is Petalinux. We need to build a complete processing system, and Petalinux needs a lot of resources on machines. You need about 50 gigabytes of disk space. You need about a 8-core system, so it's not easy to build a Petalinux system. You will also need a very stable internet connection because Petalinux works like Gentoo Linux, builds up everything from sources. So it downloads all the sources of everything and builds everything. But if you hang the connection for a little bit, you lost one element and the build fails. So it's important to have a lot of disk space, a very good machine, and a very good internet connection to build the Petalinux system. I'm currently working on that and trying to make a processing system to build to make the emulated mode of the Hello Ceilings example. That's it.
Awesome, Pedro. Thank you so much for your efforts and your work. And I'm sorry that you're struggling to get everything in place, your workstation. Fortunately, doing this only needs to be done once, and once done properly, then it is pretty straightforward. But again, for each new hardware platform, this needs to be done at least once. And Pedro, feel free to rely on me for all this effort. Feel free to push and offload you with your struggles with me. So happy to help. I'll be there for every step down the road, and hopefully we'll get to converge soon, and we'll have a second official or a second community supported platform which has essentially complied with the architecture proposed so far. So awesome to have you working on this. Thanks again, and looking forward to see more progress.
You're welcome. I will stay in touch.
Awesome, Pedro. Thank you so much. All right, so we'll have a Q&A session at the end if any of you want to give more details or ask more questions. But if everyone's fine with it, I would like to welcome officially our guest speaker. I would like to welcome Sabrina M. Neuman. And Sabrina, apologies, but I was looking throughout the whole web, a few sites in the web, and even your PhD thesis to try to see what was your middle name to say it properly, but I couldn't find it. I really couldn't find it. So Sabrina, everyone meet Sabrina. Sabrina is a postdoctoral, essentially researcher at Computing Innovation Fellow at Harvard University. Her research interests are in computer architecture, design informed by explicit environmental and domain-specific insights. She is particularly focused on robotics applications because their heavy computation demands and potential to improve the well-being of individuals in society. Everyone, please welcome Sabrina. And Sabrina, the stage is yours.
Fantastic. Thank you, Victor. Let me share my screen. And there we go. Okay. Can you see my PowerPoint?
I can.
Perfect. There we go. Yeah, hi, everybody. Again, my name is Sabrina, and like many of you, I'm interested in the intersection of hardware acceleration and robotics. Today, I'm going to talk to you about some work I did in that space. We had a paper at ASPOS 2021 that covers all of this material, so take a look. And yeah, this is work I did with my colleagues at Harvard and MIT, including Brian Plancher, who is also on this phone call, and I hope will chime in later during the Q&A. So basically, the idea is that we want agile, robust, untethered motion from complex robots, right? This would be a desirable outcome. We want these robots moving very fluidly through dynamic, unpredictable environments, and we want them interacting in real time safely with humans to do tasks in human environments. So in order to accomplish that, of course, we need real-time performance from the computation. And as you all know, robots have to do a lot of things online, many of them at real-time rates. So in the full computation pipeline, a robot might have to do a bunch of perception where it sees the world, mapping and localization where it places itself within that world, and then finally motion planning and control where it chooses a valid path through the space. Today, I'm going to focus on that last stage of the pipeline, the motion planning and control. And within that stage, yeah, it's really paramount to have real-time rates of performance, often at maybe kilohertz rates. And there are a lot of computations there that scale directly with robot complexity, especially when you have these very complex jointed robots like manipulators, quadrupeds, humanoids, or even some sort of approximation of snake-like soft robots. And so to try to do all of this fast is very difficult. Current software support is often too slow, leaving a performance gap. So for example, for nonlinear model predictive control, this gap can be like an order of magnitude. You might desire something like kilohertz rates, but only be able to perform at hundreds of hertz. And this gets worse with more complex robots. So this is the challenge. The solution, we hope, is hardware acceleration. So we would like to be inputting a robotics algorithm into some sort of maybe automated design flow, ideally, and be getting out accelerators out the other side. So today, the method of doing this I'm going to focus on has one key insight, which is that for a lot of the algorithms in motion planning and control, there's a relationship between robot morphology and computational features of the algorithms. And so, well, this applies kind of broadly across a lot of kernels within motion planning. You can imagine that the robot's motion is tied a lot to the robot's physics. And this occurs in a lot of these different sort of computations you have to do when you're considering the robot's motion. So the one we're going to focus on today is the gradient of forward dynamics, but there's also inverse dynamics, there's kinematics, collision detection, and of course, like soft dynamics, and so on and so forth. A lot of different, again, algorithms that have something to do with the robot's physical being. So the proposed solution is what we call robomorphic computing. And the idea is that we want to take a robotics algorithm that has something to do with the robot's physicality, and we want a box that we can input the particular robot and use its morphology information to create a customized hardware accelerator at the other side. So I'll take you through the steps of the flow that we came up with. So step one, we take our robotics algorithm and we go through and we identify the places where there are features of the algorithm that are tied to the robot's physical structure. And by identifying all of these places, we can create a parameterized hardware template to perform that algorithm. It's parameterized by those robot-specific features. So now we've got something that's plug and play. And so the second step is just when you have a particular robot, you input those parameters, and out the other side, you get now a streamlined, customized hardware morphology. So that's the overview. To give you some idea and make this more concrete, I'll kind of break it down. So the robot morphology you can think of as sort of broken down into a topology of robot limbs that are made up of joints and links for these sort of rigid articulated robots. And the links themselves have certain inertial properties, and the joints have different joint constraints on how they can rotate, right? And so to translate these into accelerator hardware morphology features, you have this middle layer where you sort of identify how these different morphology features of the robot tie to the algorithm. So for example, if you're looking at computations that wind up iterating through the links or limbs of the robot, these are opportunities in hardware for parallelism across, say, processing elements or data paths. And then similarly, the links and the joint types are tied directly to these sort of small sparse matrices that wind up popping up all over the place in dynamics and other computations. So directly from the inertial properties of the links, you can know constant values that are going to appear in these matrices. And from the joint types and constraints, you can know sparsity patterns that are going to appear in like joint transformation matrices. And then you can use these sparsity patterns, these constants, to streamline hardware functional units that implement the linear algebra operations, right? So we've gone and we've mapped morphology features to useful hardware accelerator features. So I'll give you an example of doing this one time for one robot manually. And then later I'll talk about how I would rather automate this process. So, the example that we gave in the paper is that we had a 7-link EWA manipulator robot, and we templated, again, the gradient of forward dynamics, and we made a processor that was parameterized by the number of links and also by the sparsity patterns in the joint matrices. And so we just went through that process. We took the limbs and links, and we turned those into parallelism in the processing elements. And we took the inertial properties of the links, and we made constant values in all of the little functional units. And then we took link and joint information and used that to determine the sparsity patterns in the matrices, which we turned into customized functional units by sort of pruning little multiplier adder trees. So again, morphology turning into accelerator morphology. And it paid off pretty nicely. So here are some highlights from our evaluation. We compared against GPU and CPU state-of-the-art baseline implementations of the forward dynamics gradient. And we had our accelerator implemented on an FPGA board. And you could see that, so the top is the single compute latency. So this is just raw compute speed up from the FPGA. And we got a substantial increase over both CPU and GPU. And then we also implemented an entire coprocessor system where we had the FPGA board talking round trip with the CPU that was, calling that function and then receiving the results. And even with all the penalty you pay for sort of IO overhead, we still maintained a speed up over CPU and GPU. So future work. All right, so having done that again once manually for the one robot, the directions to push are to expand the same approach to more robots. We think it's a generalizable methodology, so we are hoping to realize that across all sorts of different robot platforms. More algorithms, the same compute structures that we were able to take advantage of here show up in a ton of different kernels throughout motion planning. And then finally, automation. We're hoping to have a push button solution where on the one hand, you put in a robot description in like a standard URDF format. And then with no other intervention from hardware design experts, it'd be great to pop out the other end a complete hardware design morphology implemented in say Verilog, ready to go and ready to implement. So yeah, in summary, we set up this sort of flow to go from robots to accelerators. And I think that this sort of push button solution is an attractive way to sort of tame the complexity of the robotics design space to let us build up automatically optimized processors for robotics. I'm very curious to hear what everybody thinks and take any questions. So have at it.
Awesome. Sabrina, thank you so much for your presentation and for everyone's knowledge. I think Sabrina and her group, including Brian and a few others, are doing outstanding work, reading, I think, essentially much of the newest work that comes out of the good uses of hardware acceleration in robotics. So definitely worth checking and keeping an eye on their publications and work. So questions from any of you?
I have a question that probably is partially related. What's the computational model you use at Sabrina? I mean, is a stream a model? Is a standard sequential computational model, and then is basically unrolled, pipelined? Could you give us a little bit of visibility?
Okay, yeah, I think I see what you're asking. The processor that we built up, I mean, it's funny, we tried to think of this very natively in hardware, right? We were taking this algorithm and we were trying to go right to an FPGA custom template. So we were thinking parallel from the beginning, right? Every opportunity we saw to parallelize, especially along the robot's links. For the dynamics gradient calculation, there are a lot of opportunities where there are partial derivatives taken at every single robot link along the way. But it was a pretty conventional, it wasn't like a data flow architecture, exactly. It was just highly parallel. We've got processing elements that perform their computation and then hand off their results in a pipelined stage here across the middle of the processor to another pass that also iterates. Does that answer your question, or are there more specific?
Yes, it does. Thank you.
Fantastic.
Sabrina, I have a question, and you have to pardon my extraordinary ignorance about the topic. I have worked in automotive industries in the past, and with the same latency and issues they have with mission critical functions, they ended up breaking down the systems per vital blocks, where each and every of those blocks have its particular function, like for collision avoidance, for braking systems, and so forth. The way the automotive industry has solved it is by breaking down a big problem into small problem localized in those vital elements. When you break down robots per limbs and links, you came with a different suggestion to break down the acceleration, or you still have a uniquely centralized approach to the whole system?
That's a very good question. Yeah, I think that it's a little column A, a little column B. Let me flip to this slide. So, I mean, the answer is that I did zoom in on one particular sort of isolated kernel that I was interested in accelerating. What I think the use is of the robot morphology, I think that you can look at all of the individual tasks that the robot needs to accomplish, especially in the space of motion planning and control. And you can apply this robomorphic computing sort of lens or filter to the algorithms and the kernels in that space, which is to say, like, be a domain expert, use your knowledge of what the overall goal is of these kernels and whether they are manipulating the robot physically. And if they are, you can look for these opportunities to parallelize according to robot properties. Do you see what I mean? It's like just a new lens to apply wherever you would like in a system with whatever structure you have.
I understand the morphic aspect of it. The question I was trying to answer is, would we solve your general acceleration problem by disaggregating the problem, or do you have an incentive to keep it centralized?
Sorry, say that one more time.
So I think I know what he's saying, Sabrina. I think there's sort of two answers to that, which is for the actual dynamics computation, it sort of needs to be centralized, because at the end of the day, like, I need each individual computation to be done completely before I get a useful outcome. But we can separate, say, this dynamics computation, or if we're doing, say, trajectory optimization for each time step, I could compute those independently on separate processors. I could compute some of the other things I need to do, like perception and mapping. I could compute those on entirely separate processors. But for the low-level kernel of dynamics, that probably has to be centralized. And we completely agree with the sort of split approach is also potentially being useful. And really, what this work was just, we sort of went down the tree and started somewhere kind of low level for a kernel that we need to build up to these more advanced algorithms, where we might start to be able to consider some of that kind of stuff.
It's awesome. I fully understand the disaggregation and then the plug and play approach. I was just trying to be practical about what the industry would give us in terms of silicon performance, and then the chipset solution may be an easier short-term approach.
Yeah, I think that because this is such a low-level kernel, if you split it up too much, the communication delay is going to start to break any of the gains you get from splitting it up.
Very good point. Thanks so much for the presentation.
Yeah, that was a good insight, Brian. I want to shout out in this multiple computation graph, for example, the gray is I/O overhead. So yeah, here we have a two compute system hybrid approach. We've got a CPU and an FPGA board performing the one acceleration kernel, and I/O is substantial. So I think that problem partitioning across different compute elements in a system is a really interesting problem to try to solve. And I also think that, I don't know, there is incentive perhaps to move towards a full robotics processor. Oops. Ultimately, maybe there is a hardware platform almost like a GPU for graphics that is a robotics processing unit for robotics.
As you do so, have you identified some specific math that was not provided by the typical ML acceleration you will find on graphic cards and tensor processors?
Yeah, I would say that the compute that we were looking at here is a lot of operations on these sort of small and middlingly sparse matrices. So small as in they're like 6 by 6 element, all of them, because that's just fundamental to how you do the coordinate transforms. And middlingly sparse, like say 40 to 60% sparse. This is very different from the sort of matrices that you deal with in ML applications, which tend to be very, very large and very, very sparse. So yeah, I think that, you know, the sort of tensor processor units and all of the clever sparse matrix row compression and whatever else tricks that are being applied in machine learning are kind of a poor fit. They're sort of high overhead and overkill for these very small matrices. So I think these are complementary solutions. Maybe the ultimate processor has sort of TensorFlow GPU-like computation for the perception stage of the pipeline, but then for motion planning and control has a hardware accelerator that does this sort of smaller stuff.
Understood. So the FPGA allowed you to have this data flow architecture optimized for small size matrix. That's where you got the bulk of the performance.
Yes, absolutely. Yep.
Thank you.
And in fact, I've done some more work with GPUs with these sorts of kernels, and it becomes challenging because you also end up having to do a bunch of cross-product operations, which are essentially just like an out-of-order reordering of a matrix followed by a matrix vector multiplication, which is bad, just in terms of the random access sort of patterns that you end up with there. So I think there is some challenge there. You can still speed those up with some custom code, but a lot of the like pre-existing libraries that you can leverage, say like a cuBLAS or something, you know, it's just optimized for a much larger matrix multiplication and lots of little small ones. There are batch versions in some cases, but there's a lot of, it's a messy algorithm, a lot of these dynamics kernels.
So maybe connected to it, a quick question from my side. One of the things that caught my interest very early while I was reviewing your work, guys, was the results and the speedups you guys reported in your various articles. And there's a section in there that, yeah, exactly that. I love that figure. And if you go through the article, there's I think there's a number of paragraphs where you discuss essentially that these results and why GPUs suffer. And particularly, I think you cite something like that they suffer because there's high synchronization and focus on throughput. Could you guys maybe comment a bit more on this and how you guys think this could be further improved, or what are the limitations, etc.?
Yeah,
this is Brian's expertise. So yeah, go ahead.
Yeah, I've been more on the GPU side. Sabrina's been more on the FPGA side. So I've actually done a bunch of work recently. There's another paper that's like just got submitted. So there's a preprint to try to improve the GPU side a bunch. And I did get a lot of improvements. It requires a lot of reordering of the algorithm and a bunch of just sort of trying to be really smart about when do you generate a bunch of temporaries, when do you, and then we can do all these matrix vectors in parallel. But the underlying algorithm that we're trying to use here we're super optimized for a CPU, or at least they're very serial in their just sort of overall operation, which just makes it quite hard to try to extract a lot of parallelism in general on the GPU. You can do better, and I kick the pants out of this GPU version because that was my first implementation and it was not good. I thought it was good at the time. It turns out it's not good. But I still can't come anywhere close to the FPGA time on one computation. Where I can win is I can get good scalability until I run into shared memory issues where I start to blow the cache, basically. So that's sort of like one node. And then I think the other one is that as all these hardwares evolve, I think there'll be different interesting other opportunities to take advantage of different other things on the system. So, you know, every generation of GPU has some new tricks and some new, has better, you know, control logic, better caching, better, all these sorts of things. And so I think they will start to make up for their own weaknesses sometimes. And we're putting in place for both the FPGA and the GPU some automated flows to deliver code generation, which then will allow us to get this sort of optimized results across different kinds of robots. And one other point is that like the robot that we originally implemented this all for is just a serial chain manipulator, which is the worst possible robot in terms of parallelism, as it has only one limb. So what you will hopefully see on this new work as it comes out is that as you add more limbs, then we can get better performance out of GPUs and FPGAs because we can actually take advantage of that like limb-based parallelism as well.
Awesome, awesome. And I think that's why it's so inspiring, this work you guys are pushing forward, because ROS 2 today is very, very CPU centric. And many of the hurdles you are experiencing and leading the way on that path is something we as a community will also have to experience and somehow battle with. So super, super happy to hear your thoughts and your work, guys, get it presented here.
I mean, okay. That's where this all started. It all started because well, for Sabrina and I got into this in slightly different directions, but like the reason why I got into this was sort of like I tried to write a trajectory optimization algorithm on the GPU for robots, and I realized that there was no good dynamics package that I would need to use, and so I wrote from scratch this particular not so great GPU implementation for a serial chain manipulator, and was like, this doesn't scale to me writing this for every single robot, which started this whole process. And so our hope is to deliver some tools and libraries and packages that people can use to make it just easier to start to build algorithms for GPUs, FPGAs, ASICs, you name it. Because if we can deliver some of these core kernels, then you just include them. Just like on the CPU, everyone will include some rigid body dynamics library, but there just isn't one that sort of is optimized in this way. And PhysX is actually quite good, and I've talked to that team a lot, but they're trying to solve a slightly different problem in that here we're trying to solve, you know, tens to hundreds of instantiations, and so I'm doing like parallelism within the kernel, whereas the PhysX model is more like thousands of objects, and so they're actually sort of just running the CPU algorithm relatively serially, just making thousands and 10,000s of them, which is a very hard problem, but just slightly different problem.
Right. Okay, more questions? Anyone in the audience?
I have a question. My name is Ananya. I thought this was an excellent talk, very promising work. I was wondering if you have some insights on what could be the ideal morphology in terms of the number of links and the freedoms that they have. I'm trying to see the problem from the hardware side now. Given a particular hardware constraint, is there anything that can be said about the ideal morphology that suits that hardware constraint?
That's a fantastic question. I think that I can't quantitatively or definitively answer it yet, but we are building hinted at automated flows to recreate these accelerators based on robot morphology. We can absolutely put that in a loop, right? And ask, okay, as we change the URDF, number of links, number of joints, et cetera, how does that shape the compute that comes out the other side? So I think, yeah, you are just one step ahead of the curve. And the moment I have a tool, I think I can answer that question. But I suspect, yeah, that there are going to be cool sweet spots if you perform an optimization. How branchy is your robot? Once it branches, how many links in a row provide optimal amounts of straightaway parallelism that makes it worthwhile parallelizing between synchronization points? I think that's a very cool question.
I think there's another layer on that which makes this really hard to answer, which is that you then have to optimize for task within like a robotics sort of benchmarking framework. So it's both the hardware computer hardware benchmarking, but it's also like the task-based benchmarking because we can probably design the robot that's easiest to compute, but maybe it like can't do any of the tasks that you want. And so I think there's a real challenge there to figure out what the right answer is. I would imagine that, to be honest, like something like a quadruped hexapod type thing with a big arm on the top, kind of like Spot, is a nice place to start because it's relatively branchy and relatively flexible, but you know.
And by the way, real quick comment in here, and this goes back to the initial discussion I pushed while presenting REP 2008 about benchmarking. If you remember quickly, I discussed kind of like the model we're trying to follow, which is this non-functional gray box, not non-functional in the sense of measuring aspects like the system under test, meaning latency, throughput, and related. So this is one of the bits Brian was mentioning. The other one is measuring the actual system under test, the capabilities of the nudge tag or the manipulation algorithm that you're testing at that particular moment. Those two things definitely will go hand by hand. The initial proposal is just to focus on non-functional aspects because it'll allow us to compare hardware. However, there's definitely ground for cooperation in here. So if there's folks out there interested in diving deeper into this, I'm trying to set up a cooperation with the folks from Harvard to jointly push this forward. So reach out to us, sorry. And there's definitely ground for people to dive in and cooperate.
Yeah, I totally agree with everything Victor just said. I'm tremendously interested in the way that sort of a hardware or computer architect point of view here with regular benchmarking, et cetera, can tame the crazy multivariate space of robotics, where you've got tasks, you've got environments that the robots perform in, and you have the robots themselves, which all look very, very different, and the compute substrates that you can afford to put on them. So it's going to take some clever benchmarking and then some clever design space exploration tools, I think, to turn all of these things into efficient, optimal systems.
I have a small question if I have time. We are running out. Okay, I have just a question about you showed the system, which is an heterogeneous system, where I saw an ROS plus an accelerator, which was FPGA. I'm curious to know what is the current distribution of time between accelerator and the host, and just to understand what you are now doing on the accelerator. If you are capable also to do some sensing or perception, or it is just the control part of the algorithm that is on the FPGA?
Yeah, we were just looking sort of at the motion planning and control part, and in fact, this is only part of that part. So this originally came from work looking at nonlinear trajectory optimization and using that in a model predictive control type framework, which means we're doing both planning and control at the same time online. And for those algorithms, the gradients themselves are about 30 to 90% of the total computation, depending on the exact software implementation you're using, the exact robots you're working with, et cetera. And so this is accelerating that 30 to 90% chunk of the planning and control stack. It's not integrated with perception and mapping. We aim to then build on top of this eventually and do the whole planning and control problem, and then the whole robotics problem. But we're working our way up the stack.
Thank you.
And I think one last note is that when we get there, there will be a really interesting systems challenge of maybe we can super accelerate this on a GPU, for example, but you need the entire GPU for your perception computer vision. So then maybe it's actually better to use a CPU if your GPU is busy, and things like that I think will come up too. So I just want to note that, because I think that'll be a huge system level challenge eventually. But first we need to have the ability to do that test.
I think, Brian, that depends on your expectation of GPU performance over time. The performance is improving pretty radically every 18 months. So if your assumptions are based on what you see today, you're probably mispredicting the future.
I hope that the GPU performance keeps going up, since that's my main line of research, and I'd love for it to just keep getting better. I'm just saying that I think there'll be interesting, systems implications eventually when we can put every kernel on a GPU or every kernel on an FPGA, and then trying to decide what's the right balance for the whole coprocessor system.
But maybe a point to add, because I think if we're talking about an autonomous robot, safety is a relevant factor, and so typically speaking, it's a good thing to distribute algorithms on different accelerators, whether those accelerators happen to be from different chip vendors or even within the same chip. The platforms that NVIDIA builds for robotics have not just a GPU. We have separate deep learning accelerators and even small computational engines, which I don't think you tried to do this 6x6 math, but that we do have to do that kind of work as well. So it really depends on what tool do you need to do the job. I mean, asking a CPU to do machine learning inference is not probably the right thing. And similarly, asking a GPU to be a real-time hardware accelerator where it's designed to get peak computational performance is probably the wrong thing to ask it to do. It's like trying to use a hammer to put in a screw. So you really have to look at the problem you're trying to solve and what sort of hardware could best solve that problem.
Thank you, Gordon, for those bits, and I'm gonna try to cut it here, guys, because we're over time already. We can definitely follow up, and Brian, Sabrina, we will follow up on those bits Gordon just shared. Last few words from my side are about thanking Sabrina and Brian for showing up, for giving this fantastic presentation. We very much look forward to keep seeing fantastic work from your group, guys. And for the rest of you, please feel free to reach out and share your interest on contributing or on using the technology. There will be another working group meeting, hopefully very soon. And as always, all this material will be posted and disseminated in ROS discourse. So without further ado, thank you once again for the presenters. Thank you everyone for attending, and have a fantastic night. I'm gonna run to cook dinner now and have it. So guys, thank you and have a great one. Bye-bye.
Thanks everybody, yeah. Bye.
Thank you, everyone.
Thanks.